Hi, my name is Joshua Novativan, and my thermal topic today is nuclear fission. Now, the history of nuclear fission started in 1932, where the neutron was discovered. In 1934, Enrico Fermi conducted an experiment where he tried to bombard uranium nuclei with neutrons, where he thought he created a heavier element than uranium. But chemist Ida Nodak argued that Fermi didn't take into account that he might have created a new element, but she was largely ignored, and she herself didn't even follow up on the theory. In 1938, Otto Hahn and Fritz Strassmann, as well as Lise Meitner, tried to conduct the experiment as well, but Lise Meitner had to leave due to Nazi-occupied Germany, which left only Otto and Fritz to work on it, where they were trying to identify the decay products in the process, as well as the energy release. But they found barium isotopes. At the time, they didn't think that they could create new elements or old elements from breaking apart uranium nuclei. But Lisa Meitner, she proposed that they treat the nucleus as a sort of liquid teardrop, and when the neutron collides with the nucleus, it elongates and splits apart, creating old elements already on the periodic table. They accounted for this. They accounted for the change in mass as well as the energy release using Einstein's formula of E equals mc squared. Now, what is nuclear fission? Nuclear fission is just the breaking apart of a nucleus, whether it be spontaneous or from the impact of a neutron. Now, in the case of an impact by a neutron, we have that in nuclear reactors where a U-235 atom is broken apart by sending a neutron through it. Or spontaneously is when you see a plutonium nucleus break apart naturally. Now, when a uranium nucleus breaks apart from a neutron, it starts off a chain reaction because when the neutron collides with the nucleus produces two more neutrons, which then go to two other nuclei, which then causes a whole set of reactions, as you can see from the diagram. And this reaction is diagrammed as the nucleus of the uranium plus one neutron undergoing fission will create fission fragments plus 2 or 3 neutrons plus around 192.2 mega electric volts, which is roughly equal to 1.609 times 10 to the negative 13 joules. The energy released from any change in mass from the U-235 can be diagrammed through Einstein's equation, E equals delta m times the speed of light squared. Now, what are applications of nuclear energy? Mainly, we can use nuclear fission. Mainly, we can use it for nuclear energy and nuclear reactors. Nuclear energy supplies 11% of the world's electricity. And in this diagram, we have nuclear fuel rods, either thorium or uranium, being bombarded by neutron particles, heating up water pumped from a reservoir, which is kept pressurized until it reaches a steam generator, which it depressurizes it so that the steam can push a turbine to produce electricity. Nuclear energy is non-renewable, however, it is safe and energy efficient and sustainable because the amount of fuel we use is very small compared to fossil fuels. And here is a chart just depicting the operating power plant cost of different types of power plants based on their fuel type. As you can see, nuclear costs less to operate than, say, hydroelectric, or not hydroelectric, I'm sorry, fossil steam or gas turbine, but it's still more expensive than hydroelectric. And those are my references. Any questions?
What are some safety concerns using a fission reactor?
Well, some would say that radiation is a big deal, but there's actually not. There's a negligible amount of radiation around nuclear plants. There was like more radiation coming out of a 70s TV than an actual nuclear plant. So.